ask when we're trying to categorize these things, when we're trying to understand what's happening in people is, are we actually measuring the right things? Next slide. So you'll see from this past year, with these new methods of observing the brain, there are, in blue, a lot of people who meet certain biological definitions of Alzheimer's disease that end up with no cognitive impairment through their entire life. But they would have been invisible if we were only diagnosing people that came in with clinical symptoms. Understanding that disconnect, understanding why it is that some people develop the disease, what happens to them once they do, is going to be very important for any of these treatments, including the kinds that Viv was just mentioning. Next slide. So in my lab, my goal is really trying to develop new ways that can monitor these changes caused by Alzheimer's disease and see if we can find ways to inform trajectory and treatment. In one case, which I won't talk in detail about today, we'll look at functional changes with brain probes that we put into the brain to recover or to uncover functional changes in neurons and their networks over long periods of time. And what I'll talk about today are some really wonderful insights that we've had from looking at structural changes and starting to test these questions about what it is that might be causing neurons to die. Next slide. So tau tangles, which you can see here on this image, are these weird little formations in white. And neurons in red, you can see get enveloped, although the tangles themselves are usually inside the neurons. But you can see these kinds of weird structures littered all throughout even just this small section of the brain. One of the things that we'll often hypothesize when we see something that's weird in a brain is obviously that weird thing is what's causing all of the problems that we think are there. So if we see something like that, there will be a lot of treatments that are focused on trying to remove those things, especially in the case of tau tangles, where they correlate very well with neurodegeneration and cognitive dysfunction. We can develop mice models that also form these kinds of tangles. And you can see here from 3 months to 6 months to 9 months to 12 months and 24 months in white. Those are those same aggregates forming all across this mouse's brain. So the experiment that we set up initially was putting a little window above the mouse's brain, putting different compounds into its brain that glow in a way that let us track both the formation of these tangles and the loss of neurons. And this ended up being a very challenging problem. I think if you push forward, you can see a little video on the left. So if we image this, you can see there are blood vessels in red, and we can see the neurons in purple, and some of the tangles in white. So we took these, and you can imagine it kind of like taking a constellation pattern from the sky. And we try to take this image as frequently as we could, and then match these constellations on top of one another. So we could identify which neurons persisted from week to week, and then try to figure out which ones were being lost. And you can see from looking at this, this is the change across 4 weeks. And just from the outset, it doesn't really look like a lot's changing. But if you think about what's happening in a brain, it doesn't just suddenly degenerate. So it's kind of like a needle in a haystack problem. Which of these neurons are disappearing? Which of these tangles are forming? Gives us a lot of really interesting insight into this disease. So now what we're able to see, of about 1,500 neurons that we observed, 178 of them were lost. And of these, only 6 of them had this neurofibrillary tangle. So the neurons with tangles were actually 3 times more likely to survive than the ones without it. This turns a lot of assumptions about the disease on its head. This assumption that this protein that we're seeing might be a problem, rather than a solution that your brain is coming up with to try and protect itself. I kind of view this as what I call the dumpster hypothesis, or one of my colleagues in my lab calls the hoarder hypothesis. Imagine you have someone who's just got a really disastrously messy house. You won't necessarily see it from the outside, but if they order a dumpster, put it in their driveway, and you see them collecting all of their trash there, you might drive by and think, what's going on? Why do they have all of that junk? But their house is a lot more livable now. So with this in mind, if tangles are not what lets us predict that a neuron is going to die, what might? So we decided to try and look back in time, look at the neurons that died, and see if we could find features that helped us predict that they were going to be lost soon. Forward, please. And what we saw was that the neurons that were dying typically pushed away their neighbors for at least a couple of weeks before they died. And then after that neuron was lost, the other neurons moved back into the space that it took up. We don't know why this is, and I would say this is at the core of the proposal that CART is helping to fund. This idea that if we're able to find neurons that we can see are going to die in the future, maybe we can do something about it. Forward, please. And we can see if we identify in the brain all of these neurons, we see thousands of them. And after identifying them, if we observe them, about 50% of the neurons that show this characteristic die within 1 week. And the likelihood that they die is increased based on how far apart they push their neighbors. Forward, please. So that was all data from mice. Now we wanted to try and establish, does this happen in people? And we took similar types of dyes to label similar types of things. Here you can see in green we have neurons, in white we have tangles. And we started to use these advanced imaging technologies that give us the ability to image hundreds of thousands or millions of neurons across the brain. And then we can take this and use machine learning-based segmentation to identify their locations, identify whether or not they have tangles, and